will tell us about time-dependent flux backgrounds in time to be supergravity. And please take it away.
So thanks, Bruno and Filippo, for giving me the opportunity to speak here. So I'll talk about this paper that came out last December, which I co-authored with Ratul Mohanto. So it's on time-dependent flux back. It's titled Time-Dependent Flux Backgrounds in Type 2B Supergravity. So let's start with the no-go theorem of Maldacena Nuñez. So there seems to be an obstruction in obtaining four-dimensional de Sitter or Minkowski in warped supergravity compactification, at least with classical ingredients. So this is based on the assumptions that there are no higher derivative corrections. So the Newtons, and you have a finite 4D Newton's constant, and you have a warp factor which only depends on the compact space coordinates. And of course, certain kinds of fluxes, that is, if you have, let's say, a P-form flux, it should either cover the 4D non-compact part completely, or it should not have any legs in the non-compact direction. So this is what we will refer to at times as the Maldacena Nuñez type fluxes. So what can we say if we have doubly warped product spacetimes? That is, if we have a time-dependent or non-compact part dependent factor in front of this compact coordinates. So in this case, one can also move, at times we'll refer to the 4D coordinates with the hatted part and with the compact part with tilde. And of course, at times we'll move to the Einstein-frame by doing a Weyl transformation as such. So similar to the storytelling of Maldacena and Nuñez, let's start looking at the Einstein equations. So we can let's start by looking at first the Einstein equation of the external space. So we do a contraction with the metric, and again, by integrating over the 6D internal space, the the four-dimensional Einstein-frame Ricci scalar gets a contribution as such. And of course, again, this is our new ingredient, beta. And where Ti bar is this. So similarly, if we look at the internal Einstein equations, we get a contribution as such, where our tilde is the internal space Ricci scalar, and Tii bar is this object. Okay, with this at hand, to comment about the 4D Einstein frame Ricci scalar, we really need to know about the signs of this one and this one. Of course, this sign really depends on, again, here as well. So I'll first give a brief overview of the signs in the game. Here, if we have, let's say, an N-form flux with legs, let's say, R with legs R in the external space and N minus R in the internal space, this gives a contribution to our Ti and Tii bar as such, where C is this constant and this. So with this at hand, let's see what type of contributions, positive or negative, we generate. For the Maldacena Nuñez type field strengths, for example, if you cover if there are legs along all the non-compact space part, that is when R is equal to 4, in this notation, we generate a contribution similar to Maldacena Nuñez, which is negative. And if we do not have any legs in the non-compact part, you also again generate a contribution Ti and Tii bar, which is negative. Again, when beta is 0, this gives us back the original Maldacena Nuñez. So we can mix things up. Now, let's say we do not have, we do the opposite. Basically, that is, if we have legs, let's say along 1 or 3 of the non-compact space directions. So in this case, things become more interesting because now Ti and Tii bar can have either signs. And of course, for example, if you have an F3 with a 3,0 or 2,1 component, but only legs in the spatial part of the external space, then you generate a positive contribution to Ti and Tii bar, where for only for the Maldacena Nuñez type fluxes, we were only generating negative contributions. Okay, so this is the case. So now what can we say about the sign of R hat E, or the four-dimensional Einstein-frame Ricci scalar? So we have two equations to play around with. And let's say for simplicity, we have a compactification where R tilde is zero. That is, we are looking at Ricci flat compactifications. Then how can we generate a positive contribution to this object, this R hat E? So the way to do it is, if this generates a positive contribution, that is, if you have a non-Maldacena Nuñez type flux, as we showed above, then you generate a positive contribution. You can also generate a positive contribution via this. If this term is positive, then you generate a positive contribution. That is, if for R tilde equal to zero, if Ti I bar is negative, this object become negative, and you can say something about the sign of this as well. So via this analysis, actually, a four-dimensional Einstein-frame Ricci scalar greater than equal to zero is not ruled out, unlike the Maldacena Nuñez case. At least if you have non-MN type fluxes and beta in the game. Of course, one can do a more thorough analysis where they have the R tilde in the game as well, but yeah. So it's just that the four-dimensional R hat E greater than equal to zero is not ruled out. So there have been more interesting stories in the sense that when the four-dimensional Einstein-frame Ricci scalar is negative, for example, this beautiful paper where they talk about scale separation as time flows. Of course, at the four-dimensional Einstein-frame Ricci scalar, negative also has some interesting storytelling. Of course, there are many other papers by the similar set of authors on getting 4D kination from 10-dimensional Kastner-like backgrounds. And there has been studies of accelerating cosmologies from the early 2000s. That is, time-dependent backgrounds are interesting in their own accord as well, of course. So this paper by these authors will explore the study type 2A on different classes of manifolds and study the case of accelerating cosmologies in the context of type 2A. Of course, there also have been some toy supergravity models and they have constructed time-dependent backgrounds. And this is just a set of papers, but there are many more. So this lets us ask this question that what kind of four-dimensional time-dependent background is allowed in type 2B with, let's say, all fluxes or some combination of the fluxes? And on a more interesting note, can one get a four-dimensional Einstein-frame Ricci scalar greater than zero? The Maldacena Nuñez type analysis shows maybe, but is there a can we do an explicit construction? So let's try to do that in type 2B, where we have the NS sector and the RR sector, and I'll go a bit. Then we can, so the job is basically take an ansatz, solve this equation of motion, set of equation of motion, and then the background is complete. Okay, so we'll take an ansatz where, we'll take an ansatz where we set A of y, that is warping with respect to the internal space, to be zero. And we'll have this beta object that I showed in the beginning here. Of course, in the explicit constructions that I'll present, since we're stating time-dependent backgrounds, we'll make this explicitly time-dependent. And for the F5 ansatz, we have this gamma 1, which is a form on the non-compact space, and lambda 2, which is a form in the internal space. Again, for G3, we have a form on the non-compact space, and this on the internal space. And this is a one form in the non-compact space. So with this, let's see what can we say about solving the equation.
What is the rationale behind this answer? Is it the simplest thing that you can write down, so you also have legs, both internal and external, or?
The rationale is, of course, there's a spoiler. It's a spoiler. I'll say it in a bit.
Okay.
Okay. Okay, so let's first do a warm up where we do not have all of the fluxes, where we turn off G3 and you have tau to be constant. So we just have to take care of the F5 case. So F5 Bianchi actually is satisfied if this lambda 2 in our ansatz is harmonic. So, and on top of that, if we look at the internal Einstein equation, if we demand that our internal manifold is Ricci flat, and of course, the solvability of this equation actually enforces that this contraction, that is, this is proportional to G tilde Mn, and this is possible if lambda 2 here is proportional to J2. So coming back to your question, I think this ansatz actually helped us solve the internal Einstein equations better, because we were trying to take this, for example, this lambda 2 or eta 2 to be proportional to J2. And you have the internal Einstein equation factorize the x and y dependencies. So that is a rationale behind that, behind this ansatz.
Sorry, could I ask what degree is lambda 2?
Sorry?
I mean, lambda 2 is a form, right, on your internal space?
Yeah.
Or what
Yeah.
degree is lambda 2? Is it 2? I mean, 2 form, 3 form, 1 form?
It's a 2 form.
Supposed to be?
It's a 2 form.
It's a 2 form. So gamma 1
Yeah.
is a 3 form here in space
Gamma
with spatial
1,
legs?
star of gamma 1 is a 3 form here. Yeah.
I see. Okay. And so lambda 2 and star twiddle lambda 2 are both harmonic on the internal space?
Yeah. So so the Bianchi actually enforces this lambda 2 to be harmonic.
Mm-hmm. Okay, thank you.
Okay. So of course, this forces our 6D internal manifold to be Ricci flat, compact scalar manifold. Of course, I'm not saying Calabi-Yau because it could be, there's no restriction on the holonomy. It could be T6 or some K3 cross T2 or something. So the internal Einstein equation gives the condition or constraint on the 4-dimensional Ricci scalar, which is this. And of course, 4-dimensional Einstein equation that we have to solve. Again, since we are now interested in the 4D time dependent story, we'll now make beta to be time dependent. And from F5 Bianchi, I missed an N here, for an F5 Bianchi, gamma t will be fixed in terms of beta, where gamma 1 is a 1 form in the external space. Of course, star is a 3 form. This is a 4D star. So with this, we now move on to take an ansatz for the 4-dimensional metric. Of course, one can absorb this by moving to a T prime frame into this factor, of course, but we have kept everything explicit here. So now our job is, once we have solved this form equation, our job is to solve the 4D Einstein equation plus this R hat compatibility or R hat condition that we get from the internal Einstein equation. So with this, when we solve this system, we get this messy result. Of course, these alpha 1s, alpha 2 and alpha 3 can be made the same. For example, if we choose the constants C4, C6, and C8 to be the same alongside C3, C5, and C7, then you can have all of these to be some isotropic case. However, on a more interesting note, in our ansatz, if we go back to our ansatz, this beta is unfixed after solving the supergravity equations. So coming back here. However, there's a reality condition that is at all times beta should be less than some number. That is, if otherwise this becomes complex. So this is the case where we have set G3 to be 0 and tau to be constant. Now we should check if we can get r hat e to be, what is r hat e? So in our case, r hat is positive, but the Einstein-frame Ricci scalar turns out to be negative, and it is strictly negative. Okay. Of course, for completeness, I have put out the two plots that we gave in the paper, where alpha 1, alpha 2, and alpha 3 are different because we have chosen the constants to be different. And at late times, r hat e and the contribution of gamma t, that is the F5, the one form in the x direction of F5, decays to 0 at late times, such. Okay, so this was one case. In the paper, there are other cases, for example, where we turn on, for example, G3 and take tau to be time dependent. There's of course other cases, but for completeness, I'll just present one of the cases. That is where we have all of the fluxes to be non-trivial. In that case, we turned on the 3,0 component of G3 alongside the F5 components, because our G3 had two components, 1,2 and 3,0. So once we solve the supergravity equations in our setup, we get this form for the objects in our ansatz, where lambda 2 is again proportional to J2 because we were demanding the internal space to be Ricci flat. And on a more interesting note, this alpha 1, alpha 2 can be made the same by a choice of this constants. However, alpha 3, in this case, that is one of the directions, cannot be made to be the same as the other two. So there's some anisotropy in this solution where all of the fluxes are turned on and you have time dependence in all of them. And sadly, again, we have a 4D Einstein-frame Ricci scalar, which is negative. How much time do I have?
You've spoken for 17 minutes, so another 8.
Okay. So maybe I've spoken too fast. So in this case, of course, there's no restriction again on beta, and r hat e decays to 0 at late times. And this is one of the cases that we pointed out. So what we have done is we have also checked the energy conditions in this setup. That is, we have checked the weak energy condition, the strong energy condition, and the dominant energy condition. And in both 4D and 10D, we see that our constructions do not violate any of the energy conditions. So, yeah. So lastly, I'll discuss some of the things that came out of this. Is in all of the cases, what we were trying to do is the strategy was the same. We were trying to look for internal manifolds which are Ricci flat. And the Ricci flatness actually forced us to take the two forms in the internal space to be proportional to the Kähler form. And that gave a restriction on the internal manifold, which becomes a Ricci flat Kähler manifold. And this is common to all of the constructions. And when we have all of the fluxes turned on, there seems to be some anisotropy in a sense that all of the directions cannot be made the same. Sorry, excuse me. So all of the directions couldn't be made the same. And one could also, So one question to ask is that is there some kination type story going on? So we checked the Kastner condition. So you can have at late time some Kastner-like solutions. However, I say Kastner-like because you can only satisfy one of the Kastner condition. The second one is not satisfied in this setup. So one of the things that we didn't do in this paper is that we turned off A of y. What could have been done is, what could one do is that turning on A of y and study this background in more detail and see how the story goes, and maybe constructing a doubly warped time-dependent background. Of course, one could study the moduli space of these constructed backgrounds as well. And lastly, what can we say about the positive Ricci scalar of the 4D Einstein-frame metric? We were looking at Ricci flat compactifications, maybe turning on this, maybe having non-MN type fluxes alongside non-Ricci flat compactifications might help in the story. That's something that we are trying to understand more. Thank you.
Thank you. So are there any questions? Since you ended quite early, there is a bit more time to discuss. I see Thomas.
Yeah, I didn't.
I have a question. So,
yeah,
did I understand correctly that the motivation was to see whether you could evade Maldacena Nuñez no-go with time dependence, so that you were interested? It seemed that you were interested in a positive R in Einstein-frame, the 4D metric in Einstein-frame. So, and I guess you are interested in that because positive R is guaranteed if you have a cosmology where k equals 0. So, and which is accelerating,
yeah.
right? But I think we know the answer to that question, right? So if I stick to your framework, say Ricci flat internal manifolds, and if I put fluxes homogeneously in such a way that a consistent truncation is to just have the volume modulus run, then I need to do only one thing. I need to send the volume modulus up the flux potential. Because then if it starts moving up, at some point it turns around, it goes backward. And at the point of turning, there is cosmic acceleration. This was pointed out quite a while ago by Emparan and other people. So we know the answer to that question. It is possible to get cosmic acceleration. It's just that nobody found more than 2 or 3 e-foldings. That's like roughly the amount that you can have. Yeah, I just wanted to point it out.
Yeah, sure. I think the motivation of the paper was constructing a time-dependent background in type 2B, but I started with the motivation, that is, I started with something that maybe motivating Maldacena Nuñez might be better.
I see.
Yeah.
Thank you.
But I didn't know about the paper.
Please hand up. Ahmed, hi, Aviral here.
Hi.
So maybe I missed it, but the metric ansatz that you picked had beta as a function of x, but then after solving the equations, you said beta as a function of t is remaining unfixed. So when did you put the explicit dependence on t?
So this x is actually, okay. This x actually means all of the non-compact space coordinates.
Okay, I see.
Not just the spatial ones. It's all of them. But at the end of the story, we were interested in constructing time-dependent backgrounds, so we set it to a function of time.
So what remains unfixed is beta as a function of x, right? In general, in your solution?
I mean,
and not the t.
Yes, I mean, we solved it for t, but I guess, yeah, beta of x would be fixed as well.
Okay, cool, thanks.
I mean, we set all of the other dependents if you want to be trivial or zero.
Okay, thanks.
Anybody else?
Maybe related to Thomas's question. So that you showed the pictures, and perhaps I missed the answer. But can we consider these as accelerated solutions?
No. The solutions we got are not accelerating solutions. But there has been some progress.
Well, this must be related to the fact that you don't violate the strong energy condition, right? I mean,
Yeah.
Because after all, the earlier view on the Maldacena Nuñez is by the observation by Gibbons that the strong energy condition really is to blame, right?
Yeah.
Sorry, I interrupted you.
Yeah. In our setup, we do not violate, but what we were thinking is that if what we were calling this non-Maldacena Nuñez type flux, maybe this helps us in some way getting a contribution which is positive to the Einstein-frame Ricci scalar. But the ones supergravity equations did not allow us to have that, but I don't know. I'm not sure what we were missing so that we could not generate positive Einstein-frame Ricci scalar, which is great.
I mean, if the strong energy condition really is key, then the Romance mass, the cost of something like broken record, but the Romance mass will be what breaks a simple thing that breaks that doesn't obey strong energy condition string theory. So perhaps that might help in future work.
But can I comment on this? Also, sorry to interrupt, but the strong energy condition is violated with time dependence. So you can have a 10D theory that obeys strong energy. The moment you compactify on a time-dependent manifold, you typically violate strong energy condition. And so normally the standard thing is that whenever your effective potential has a positive region, cosmic acceleration is actually generic. As I said, you only have to send a scalar upward. At some point, it will turn down. And at the point of turning, there is cosmic acceleration. And so the moment you say Ricci flat, no D-branes, no orientifals, fluxes, the potential is actually strictly positive.
Sorry, maybe confused by your language. Sorry to interrupt. The strong energy condition is not something that you need to check on the solution. It has nothing to do with whether the solution is time dependent or not. I mean, it's something about the action, right? You check it once and for all, and then you play with the action.
Well,
I mean, it's a condition on T mu. Probably in your language, what is really crucial is this fact that you're saying that you need to go up the potential, and at some point you go to a positive region of the potential. Is that what you?
I'm just saying that any effective field theory that uses fluxes in a compactification can break strong energy condition in a certain region of the potential.
From the 4D point of view, you need to check the sign of the potential for the strong energy condition.
But it's strictly positive in this case. I have Ricci flat internal manifold fluxes. My full scalar potential is strictly positive.
Okay. I guess in this case, it would, maybe it would be illuminating to translate what you're doing in terms of an effective field theory to compare with those guys. Most of the scalars will be zero actually in fixed at the vacuum, but then you might have some axioms activated because of the fluxes. Might be interesting to compare with the literature that Thomas is
sure.
Yeah, on this note, you were saying that these solutions look like Kasner, right? Well, quasi-Kasner, right? You only satisfy one condition.
Yeah.
Right? You
At late times.
Could there be some, asymptotically some Muller solution where you have rolling scalars that are maybe dualized forms or something? Because they're right, you satisfy one Kasner condition, but you also have a scalar and so on.
Yeah, I think so. Yeah. Yes.
Okay, are there further questions? Otherwise, it's been exactly half an hour, so we can thank Ahmed again. And go on with the second talk.